So thank you for having me. How's everybody doing today?
Good.
Good. Yeah, all right, great. Thank you for coming. I had a great time this morning listening to wonderful presentations. So I'm returning the favor, hopefully giving a wonderful presentation, but you'll be the jury on that. I invite questions at any time. This is research in progress. It's mainly sharing questions and results that we have, but these results are preliminary. That we feel that there are many low-hanging fruits, and we want to share it around. And there are many questions we don't have the answers to, so it'll be good to hear from your ideas, comments. Can everybody hear me? Those in person? Can everybody online hear me? If you can, thumbs up. Okay, great. All right. Okay, so let's get started. So I'm going to talk about graph decomposition and what we call the matrix apportionment problem. Let me give credit to my co-authors. So this is based on a paper that is posted on arXiv and submitted in review right now, written with Antoine Clark, who's at JHU, Brian Curtis, and Leslie Oben are both at Iowa State. Okay, so what am I going to talk about? So let me set the stage using a problem that's very natural to us. So if you're given a matrix n by n, assume the matrix is normal. One way to think about diagonalization of matrices is to think about acting by conjugation on your matrix A to make your matrix diagonal. Now, action by unitary conjugation does not change the Frobenius norm of your matrix. The Frobenius norm doesn't change. So what this action can be seen as doing is concentrating the mass of the entries to make the fewest entries as large as possible. So imagine you have entries that are smeared around, and you want to concentrate them to make the largest entry as large as possible. So if you write that problem is completely equivalent to diagonalization. And the largest value you can get is the largest eigenvalue. So if you ask, I want to use unitary actions to concentrate the entries to be as large as possible, the largest you can get is the largest eigenvalue. The problem we're interested in is the reverse. I give you a diagonal matrix, or any matrix for that matter, and your job is to find the unitary matrix that spreads as much as possible the wealth. Okay. Therefore, apportion. Okay. And we ask how much harder that problem is compared to diagonalizing. And the take-home message is, well, diagonalization is easy. We've been doing this ever since man can walk upright. Apportionment seems to be incredibly hard. Okay, and it reduces to a lot of problems that are well known, have been studied for a long time, that we still don't know how to solve. So we want to compare both settings. Now, why am I talking about the unitary group? Unitary group is a good place to start. It doesn't change the Frobenius norm, but you can pick any subgroup of the general linear group. So think invertible matrices. So U can be invertible, and you're acting U times A times U inverse, and you want to make the absolute value of the largest entry as small as possible. That's what we're going to do in the apportionment version. First, let me stop here. Make sure any questions. Any questions? Okay, all right. So let's get started. So let's do some examples of apportioning. If I change the soup by an inf, what does that mean? So if I give you a group G, and G is an arbitrary subgroup of invertible matrices with complex entries, we say that A is G apportionable if there exists an element of G for which, when you apply UA, U inverse, all the entries have the same absolute value. So you've been able to smear the well equally among all the entries. So if that happens, you say your matrix is apportionable. What are examples of apportionable matrices? First example is this one. 2, 0, the entries are concentrated here. It's an easy exercise that you can find a unitary matrix that actually takes you to the all-in-one matrix. And the exponential e to the I pi of this matrix is also apportionable. That's a nice exercise. So what we want ultimately is to start from something like this and end up with a matrix whose entries are all in absolute value equal to 1. So we don't require that all entries are equal to 1, but all entries should be on the same unit circle on the complex plane. Any question? So that's the
Frobenius norm is preserved, right?
So if you act by the unitary group, then the Frobenius norm is preserved. But if you act from any arbitrary subgroup of GLN, it's not necessarily preserved. Okay? And for most of the result, we're going to prove there will be over unitary groups. So unitary apportionment is where we prove most of the results. But we're interested in the general linear group apportionment.
So in that case, at least we know what the maximum absolute value will be.
Yeah. So exactly. So we know that if you're working over the unitary group, when the matrix is apportionable, the smallest the entry should be Frobenius norm divided by n. Yeah, by square root of n. I think it's Frobenius norm divided by n because you're looking at an n by n matrix, so there are n square entries. So there's Frobenius norm squared divided by n squared, you take the square roots, that's Frobenius norm divided by n. Okay, all right, thank you. That's a very good one. Any other questions? Okay, all right. So what I promised you that this apportionment problem is hard. Why is it hard? So Frobenius problem is this problem of apportionment is hard because it really easily reduced to what I call the Riemann hypothesis of linear algebra. So that's my statement. That's not anybody else. One of the hardest problems in linear algebra is proving that there exist Hadamard matrices for every multiple of 4. What is a Hadamard matrix? So let me take a vote. Right? How many of you have heard of Hadamard matrices before? If you have, raise your hand. If you have not, you're in for a treat. So a Hadamard matrix is a square matrix where the entries are only 1 and -1. And every row is orthogonal. They form an orthogonal basis. These matrices are incredibly useful as combinatorial objects. And in some sense, they're plentiful. In some sense, they're rare. Jacques Hadamard himself thought about Hadamard matrices. Now, why did Jacques Hadamard thought about them? He actually pointed out that if the absolute value of the entries of a matrix are bounded by 1, then these matrices maximize the determinant. So you could, in theory, find Hadamard matrices by using gradient descent on the determinant polynomial. Unfortunately, determinant polynomial is a polynomial n-squared variable. It's not a good way to proceed. It's very easy to see that to be a Hadamard matrix, your number of rows has to be a multiple of 4 or 2. He conjectured, it's not really him who conjectured, but it's attributed to him, that for every multiple of 2, there exists a matrix with entries 1 and -1 that's orthogonal. And when I say orthogonal, I mean you multiply by the transpose, you get n times identity. We do not know how to prove this conjecture. And it's surprising, we tried very hard. There's some families of multiple of 4 for which we know the answer. But there's some relatively small values of multiple of 4 for which we have not found Hadamard matrices. So this is a very hard problem. And it can be attacked from either the algebraic side or the combinatorial side. And this combinatorial side is the second theme of the talk, this so-called graph decomposition. It was shown later on that a Hadamard matrix exists if and only if you can decompose the complete graph on n vertices. So a complete graph on n vertices is a graph where between any 2 vertices there is an edge. So they show that the Hadamard matrix of size n by n exists if and only if you can decompose the complete graph on n vertices into a union of complete bipartite graphs. So complete bipartite graph means you have a group of students, size n, a group of professors, size n, and you can match a student with any of the professors. Okay. There's enough professors to match any student, and all the edges are possible. So you can decompose your graph into complete bipartite graph, such that every single edge in your complete graph occurs in n over 2 copies. So if I look at the edge 0, 1, edge 0, 1 has to occur into exactly 2 copies of these bipartite graphs. If I look at edge 0, 2, edge 0, 2 has to appear in exactly 2 copies of these bipartite graphs. So the decomposition problem is I give you a complete graph on n vertices, find a decomposition into complete bipartite graphs, such that each edge of the original graph appears exactly into n over 2 distinct copies of these bipartite graphs. So that's the decomposition problem. I give you a graph, and your job is to find a union of some template graphs that cover the graph with some combinatorial constraints. pieces. So combinatorics have been interested in this problem for a very long time. It turns out it reduces to searching for Hadamard matrices, and both problems are known to be very hard. Now, it's not known to be NP hard, but we suspect that it is. There's no proof that Hadamard search is NP hard. There seems to be a question in the chat, so let me check quickly.
Yeah, actually,
Okay, so this is not.
I don't think so.
Okay, this is not a question. Okay, all right.
Yeah.
Let me know if you see a question.
Actually, I'm just wondering
Okay, all
why.
right. Any questions about the Hadamard search problem? All right. Now, why do I point out the Hadamard search problem? I point out the Hadamard search problem because the Hadamard search problem is an example of apportionment. Hadamard matrix, if it's symmetric, has real eigenvalues. And because it's orthogonal, the eigenvalues can only be 1 or -1. So if you want to know whether a Hadamard matrix exists, okay, all you have to ask is whether one of these diagonal matrices, so you first put -1s for a certain k, and then you follow by +1, okay, and you ask, is this apportionable using a real orthogonal matrix? If the answer is yes, a Hadamard matrix exists. If the answer is no, you add another -1 until you get to n/2. So basically, there are n/2 queries of this question that you need to ask. And after you made those queries, if the answer is no, there is no symmetric Hadamard matrix of size n. So the problem of finding the decomposition or finding a Hadamard matrix is a special case of the apportionment problem. So this is the first hint that apportionment problem is not easy. Any questions? So, Hadamard matrix can only have eigenvalues, negative and positive. You sort the eigenvalues, sort the eigenvalues, and therefore it's a bunch of negative plus a bunch of positive. You only need to make n/2 + 1 queries, okay, as opposed to the 2 to the n. And if either of these queries returns yes, there's a Hadamard matrix. If the query returns no, there's no Hadamard matrix. All right. And we do not know how to answer this problem.
You said something about the symmetric case, right?
Yes, this is symmetric. So the reason we're restricting to symmetric is because we want real eigenvalues. If it's not real, then the eigenvalues are on the unit circle, and that's infinitely many choices. So real Hadamard matrix is symmetric. I'm talking about symmetric Hadamard
So you
matrices.
could answer only the question about
Real, that's symmetric. Yeah, that's correct. That's correct. If you want general Hadamard, there's a version of it, but it's more complicated. Absolutely. Thank you. That's a good question. Okay, but are there other problems that reduce to this so-called apportionment problem? There's another fantastically hard problem that reduces to apportioning, and the problem is the following. I give you a matrix B. It's D by n, and I tell you that each column has unit length. Each column has length 1. And what I want to ask is whether it's possible to find D equiangular lines. These are lines in RD that, we want lines in, yes, lines in RD, lines in Rn, line in Rn, that have equal angle between them. Okay, think orthonormal sets. That's an example of the equiangular lines. This is a very well-known combinatorial problem, also very hard to solve. Now, if you're equiangular, that means that when I compute B times B star, I get identity, so to speak. The B times B star is computing the angle in between them. If you shift the diagonal entry by the cosine, the angle, you get an apportional, you get a matrix where all the entries basically are equal to the cosine. Okay, so this tells us that equiangular line problem is also as hard as apportion. Okay, so these are two problems that are very hard to solve, which reduce to apportioning. So this tells us that it cannot be the case that apportioning is easy. Because if you could apportion easily, you could solve very easily these problems, and these are still open problems that people are investigating. Okay, now to get to the next segue, if we want to prove theorems about apportionable matrices, you want to leverage on what we know, and what I know is graphs. So I'm going to describe functional graphs. So the true story for me, per se, was that I was trying to prove theorems about graphs, I realized that it connected to diagonalization, and I was really hoping that linear algebra was going to provide proofs for theorems I wanted to prove for graphs. It turns out that I was not lucky. The only examples, non-trivial examples that I could construct in linear algebra came from graph theory. So I'm going to do a detour and talk about some graph theory. So let me describe what we call, in the Baltimore School of Combinatorics, functional graphs. So a functional graph is a graph on n vertices where every edge describes the image of the domain. So I want to think about a function from Zn to Zn. Think Zn is all integers from 0 to n minus 1. And there is an edge from I to f of I. So here's an example of a drawing of a functional graph, where I take 0, f of 0 is 1, so there's an arrow that goes from 0 to 1. I take 1, there's an arrow that goes from 1 to 0, so f of 1 is 0. If I take 2, there's an arrow that goes from 2 to 1, so f of 2 is 1. And if I take 3, there's an arrow that goes from 3 to 3, so f of 3 is 3. So if I give you an arbitrary graph and I ask, does it describe a function, the necessary and sufficient condition for recognizing a functional graph is that every vertex must have out degree 1. If I draw a graph and one vertex has out degree 0 or smaller than 1, it is not. Smaller or bigger than 1, it is not a functional graph. So just to make sure we're on the same page, let me draw a graph. Okay. Okay, so let me do this. Is there a way of placing arrows on this graph to make it functional? Yes?
Yeah, that's actually the question I was going to say. That if you have an undirected graph,
Yes.
can you answer the question whether...
It turns out you can. It turns out you can. Those are excellent questions. But, okay, let's warm up with this, and then I'll answer your question. So if I start with this graph, okay, so I need to put here 3. Let's go in columns. Do you suggest any arrows on the edge, 2, 3?
Well, 2 to 3, obviously.
No, so we're starting in order, so you're first. So what do you suggest for the arrow on 2 to 3?
Let's go 2 down to 3.
2 down to 3. I agree. Next person, what do you suggest for the arrow 0, 3?
3 to 0.
3 to 0 is probability 2. There's 1 half. Okay, okay. All right. Next person, what about the edge 0, 1? What do you suggest for edge?
1 to 0.
1 to 0. Okay, 1 to 0. That's fair. Next person, what do you suggest for edge 1, 3?
I lost.
No, 1, 3. Okay, so what edge would you change to have a fighting chance? Which edge would you change?
Let's say 0 to 1.
So 0 to 1. Okay, I agree. Okay, so I'm sorry for the person who said, okay, we're gonna do 0, 1. Okay, next person, what about the edge 1, 3?
1 to 6.
1, 2, 3. Okay, so now let me answer Radu's wonderful question. If you have more than n edges, there's no chance you can win. Because there has to be exactly the number of vertices matches the number of edges. Now, if you have n edges, what are they going to look like? The picture for a functional graph is trees growing on cycles. So what it will look like, basically planets with trees growing on them. So you have vertices, let me draw some cycles. Let me do this. So you get the cycles. Once you have a cycle, you orient the cycle so it's a directed cycle, just like we do with this symmetrically. Okay. So these cycles have to be directed. That's the only way you can get every vertex to have out degree 1. It has to be directed cycle. If you flip any edge in here, one vertex is going to have out degree 0, or one vertex is going to have out degree 1, out degree bigger than 1. Okay, so directed cycles. But what else can happen? You can have a tree that grows on the cycles. And this all functional graph look like this. It's trees growing on cycles. You have to allow for fixed points, but all functional graphs are unions of cycles on which trees are growing. So does that answer your question? So you have a bunch of cycles and then trees grow on these cycles. Some cycles have no trees, but they look like this. This is a characterization of all functional graphs. These are the set of all graphs that have exactly Exactly, and edges and vertices, and every vertex is out to do. Any questions on what functional graphs are?
Well, at some point, is there a matrix language equivalent to what you just described?
Absolutely. So in matrix language, you draw the adjacency matrix, and every row has to have exactly one non-zero entry equal to 1.
That is a necessary condition. To
Yes,
start with. Is it sufficient?
it's sufficient. It is absolutely
Because
sufficient.
you go from row
Row
index
to column.
index.
That's correct. And that's the function. That's the function.
I see.
So that is in matrix language the complete description of these so-called functional graphs. All right. Okay. So we pinned down what the functional graphs are. How are we going to use them? So I want to now describe a nice decomposition problem. And this is tribute to, remind me your name again? Stratos. This tribute to Stratos, who gave me a wonderful presentation today. So I'm going to return the favor and talk about some special decompositions. Let me do this. So this is the part where, unfortunately, those who are not here don't get the full experience, but I think they will see, I will write large enough so they can see the board.
Maybe if you just blank your.
But they can see with the camera, right?
Okay, yeah.
Yeah, you can see me? Okay, I'll write. Okay. So I'm going to write a decomposition problem. So I'm going to consider a 3x3 matrix. The entries of the matrix are going to be symbolic variables. So here is a 0, 0. Here's a 1, 0. Here's a 2, 0. Here's a 0, 1. Here's a 0, 2. Here's a 1, 1. Here's a 1, 2. Here's a 2, 1. Here's a 2, 2. So this is a matrix. So typically, if you think about this matrix, I want to think about the first column as edges of a graph. So column 1, column 0, and right here, column 0, column 0, describes the following graph. 0, 1, 2, 0. Why? Because I think about this edge as the edge A0, 0. I think about this edge as the edge A2, 0. I think about this edge as the edge A1, 0. Okay. Now, what's interesting about this graph is that if I add 1 modulo 3 to all the vertices, I get the second column. Okay, so I want to add 1 modulo 3 to all the vertices. So if I do that, let me ask for help. You're never supposed to do things live on the board without help. Bad things can happen. I'm superstitious, so let me ask for help. We have to skip it after we said that. So help me out. So I want to add 1 modulo 3 to 0. What do I get?
Like 1.
We get 1. It's not a trick question. Next person, I add 1 modulo 3 to 1. What do I get here? You get 2, thank you. And next person, I add 1 modulo 3 to 2. What do I get?
0.
You get 0. So adding 1 modulo 3 to the graph you have here gets you this graph. Everybody sees? Now I'm going to do the same thing. I'm going to add 1 modulo 3 to this graph and see what graph I get. So now back where we started. So if I look at the next graph, I add 1 modulo 3 to the vertex 1 here. Which graph? Which label do I get here? We get 2, thank you. Next person, if I add 2, 1 plus 1, 1 plus 2, I get 0, thank you. Next person, what do I get if I add 1 modulo 3? We get 1. We get column. All right. So here, it seems like a nice property that if you take the matrix and you act by the cyclic group on the labels, you get all the different columns. So Ringel asks, for which graph is that property true? For which graph can I put in the first column, act by the cyclic group, and generate all the slices? Now it's important, these edges should be edge disjoint. The graph should not share any edges. and they should account for the complete graph. So what do I mean by the complete graph here? I mean the following graph. Okay, the three, so there's three of them. So let me put 2 here. So the complete graph looks something like this. I'm going to put the 2 directions for the 2 edges, and then you have these loop edges. Every edge in the complete graph is accounted for by one of the edges in this. So this is called a graph decomposition. Graph decomposition, these are very special graphs, they're cyclic graph decomposition. It's the decomposition where the components are edge disjoints, and the action of the cyclic group on the first one generates all the others. Right? Not all decompositions have this property, but we're going to be interested in decompositions that have this property. So let me show you that there are other decompositions that have this property already for the 3x3 matrix. So what's another one? Let me show you another one, and we go back to the slides. So what's another decomposition? If you've never thought about this, I'll give you a few minutes before I spoil it for you. So here's another decomposition. Instead of putting 2, 0 here, so let me erase these guys. Instead of putting 2, 0 here, instead of putting 2, 0 here, I'm going to put a 0, 1. Bear with me. Now let me draw the graph that this looks like. So if I draw the graph that this looks like, the graph looks like I have vertex 0, I have vertex 1, I have an edge that goes from 0 to 1, I have an edge that goes from 1 to 0, and I have a loop edge. Yes? Okay. So now I want to again act by the cyclic group to see what graph does it generate. So let me ask for help. If I add 1 to the vertex label, it's not going to change the structure of the graph, you only change the vertex labels. So next person, who's next? I believe you're next. Help me out. What are all the labels? If I add 1 modulo 3.
1.
This becomes 1, and 2. This becomes 2. So here, the edges that I have are A, 1, 1. So if you ask, why did I put 1, 1 here? Why didn't I put it here? I'm adding by 1 both, so I shift down. So I add 1, I'm shifting down, that's why I put it here. Okay, and what other edge do we have? So this edge is going to go back, up here, so this is going to be 1, 2. And then here we have A, 2, 1. So you see, these two graphs are edge disjoints. They do not share. And by acting by the cyclic group, I've generated a column that is completely edge disjoint from the other. Yes? Okay, let me act again by the cyclic group. Okay, so let me ask for help. Next person, help me out. If I add 1 modulo 3 to all these vertices, what label do I get? Oh, no, you're next. Yeah. So we got 2, 0. Okay, so if I write the graph here, this came here to be A2, 2. Okay, this guy goes here, become A 0, 2. Thank you. And next person, now it's your turn. What do I put here?
I think you have a.
Yeah, so it's this guy going down.
Yeah. That should be a 2, 0.
2, 0. Very good. Alright, so now I can tell you the fantastic conjecture that Ringo made. Ringo noticed that if you actually look at the undirected version of this, it's a tree. If I don't care about the bidirection, this is a tree, 0, 1. It's the only tree on 2 vertices we can go up with. So Ringo made the fantastic conjecture that if you have a graph, okay, 2n minus 1, and in this case 2n minus 1 is 3, and in this, if you take 2n minus 1 to be 3, that means n is equal to 2. That's why our tree only had 2 vertices. If you take k2n minus 1, this trick that I've done, you can do it with any tree on n vertices. So I give you a tree on n vertices. There is a way you can label the tree such that all the columns, all the slices are edge disjoint and completely decompose the complete graph. Is the statement clear? That I can decompose the complete graph into edge disjoint copies of a template that is isomorphic to any tree you give it. So the adversary picks a tree on n vertices, and I claim I can pick a column made of the edges of that tree, and the action of the cyclic group generates all the others. This is the problem which I was motivated by. This was raised in 1964, and a lot of ink has been spilled trying to figure out whether that statement was true. So I worked very hard to reduce this to apportioning. And I was hoping apportioning was going to tell me how to find the decomposition. Bad news, apportioning did not tell me how to find the decomposition. I found the decomposition some other way, and that gives rise to all the non-trivial results I know about apportioning. So let me share those with you now. Okay, all right. So it turns out that this problem that I described of decomposing can be reduced to a very special type of labeling. And these are called row labeling. It turns out that what's important in the decomposition is how you choose your first column. And what Rosa showed is that to pick the choice of your first column, you just need to pick a functional graph for which basically the absolute value along every edge is a distinct number. So I'm skipping some steps here in the interest of time, but there's a way of recognizing that your first graph is correct. And maybe I should explain this one in the case of the tree. So how do you construct this first template? Let me actually show what it means and the problem that we're interested in. So suppose the person gives you the following tree. Now, what Rosa showed is that if you actually want to be able to find this cyclic decomposition, it suffices to find a very special labeling of the vertices. And that labeling has to be achieved such that, let me actually do it here, that when you take the absolute value difference along the edge, you get a distinct number. So the absolute value between 0 and 3 is 3. That's the edge label for this edge. The absolute value between 3 and 1 is, I think you're next, 2. So and the absolute value for this edge is
1.
There you go. Now if I had a loop edge, let me put a loop edge just for the fun of it. It doesn't matter where you put the loop edge, the absolute value is 0. So if you have a labeling where all of these absolute values are distinct, this graph is a proper graph for the first column of my matrix. And adding 1 would generate all the slices and it will be edge disjoint. This labeling is very special. It's called a graceful labeling. So the problem of decomposing a graph reduces to the existence of a graceful labeling of every tree. So you can play this game with your nephew, niece, son, daughter, cousin. Draw any tree and tell them to come up with a labeling such that the absolute value are distinct along every edge. It is very difficult to do in general. And we do not know a polynomial time algorithm to do it. The proofs that we know are non-constructive. So they're non-constructive proof showing that these decompositions are possible. Now, here are some examples of this labeling.
Default, but leave meeting button.
You don't need to be a tree. There are graphs like these that are functional. And you can see that originally the edge label 1 repeated. But if you relabel them carefully, no edge repeats. So this is a valid choice for the first column of the decomposition. Everybody got it? Okay, so what are we able to show? It turns out that all the non-trivial examples of apportioning problem we come up with are related to this problem. So we find edge disjoint decomposition of the complete graph, and we show that the corresponding, you can use these to construct apportionable matrices. So here's the first non-trivial theorem. So we say, take any tree you want. Look at the adjacency matrix of the tree and the adjacency of the transpose, and add them, except if there's a 1 at a location, don't add 1 plus 1. Instead of doing 1 plus 1, you do 1 or 1. So 1 or 1 is 1, as opposed to 1 plus 1. If you do this operation between the adjacency matrices, add a couple of zeros, take the tensor product, this matrix
Dim 4Y
is
has left the meeting.
apportionable if and only if the graph has a graceful edge. So it turns out that the apportionment problem easily reduced to finding these labelings and decompositions for our complete graph. Okay, so you can say one way of generating apportionable matrices is to take matrices whose entries are already ones and negative ones and compute their eigenvalues. But that's a bad source of examples of apportionable matrices. You want some combinatorial construction that gives you apportionable matrices, and here the result is, for any tree that you pick, this tensor product construction gives you apportionable matrices, and you would have not expected this. Okay. All right. What is another non-trivial family? Let's see. Okay, so this is this is a sketch of the proof of the apportionability. I will skip this in the interest of time. These are the groups. Let's get to some interesting results. So up until now, I gave you problems that are very hard that we solve in order to say something about apportionability. So what can we say about apportionability in general? The bad news is we cannot say much in general, but the very little we know, I will share with you so you can add to it. First of all, we know that all rank 1 matrices are unitary apportionable. If I give you a matrix that is rank 1, we actually have an algorithm to find the unitary matrix that would apportion it. So
You're flat and you equalize the entries right up there.
so you need to pick your unitary matrices very carefully, and basically you want to get an outer product of a vector that has all ones, and another one which has signed version of ones. And it's not trivial to show that you can always do it, but it's doable.
Can you not rotate so your vector and the line along?
So you have two vectors, right? Rank 1 matrices can always be written as U outer product V.
Oh, not symmetric.
Not symmetric, no, this
Okay.
result is not symmetric, yeah. So I give you U outer product V, and the claim here is that you can find a U that would rotate, conjugate this, where all the entries have the same absolute value. So if you have U, then your argument works, right? But if you have the V, you have to be a bit careful. But you solve a quadratic equation to find that. Okay. So that's not so hard, and the only reason we prove this first is because we asked the question first. You would have proved this if you thought about this first. Second, PSD matrices is apportionable if and only if the rank is less or equal to 1. And that's not too hard to see. So if I give you a positive definite matrix, if the rank is 2, it's not apportionable. And the proof really comes from the fact that when you multiply matrix by its transpose, you're computing inner products of vectors with themselves. And you're basically getting cosines. And the only way all the entries have the same magnitude is if the angles are the same within themselves. So it tells you that the vector has to be a copy of itself in the rows, which gives you that apportionability for PSD implies rank 1. And rank 0 is easy to see that that's apportionable because all the entries are 0. All right, what else can we show? Well, we want some negative results, which matrices are not apportionable. We believe that almost all matrices are not apportionable. Whereas we know that almost all matrices are diagonalizable, we suspect that almost all matrices are not apportionable. If that conjecture is true, then you put our name on it. If that conjecture is false, then I just heard it from somebody else. The point here to prove that matrices are not apportionable, this simplest family we can come up with, is to look at what happens when you shift a matrix by the identity matrix. And then it's a follow your nose kind of proof. If you shift by a constant times the identity, if the constant is large enough, you can't be apportionable, and we write that constant, the constraint of the constant like this. It's not very difficult, it's not particularly beautiful, but unfortunately, although being sufficient, it is not necessary. There are non-apportionable matrices that does not meet this condition. But the beauty of this result is that it already shows us that there are a subset of matrices in the complex plane of measure positive that are not apportionable. And this you cannot find for diagonalizability. Because almost every matrix is diagonalizable, there is no positive measure set of the complex plane that contains non-diagonalizable matrices. But this is already true for non-apportionable matrices. Okay. All right. Now, as I said, these results about decomposing the graph, the example that we talked about, followed from results from Richard Montgomery, Alex Progowski, Ben Sudakov, and Peter Kivash. They were the first ones to show that the decomposition that we want for tree always exists. And these give us our non-trivial families of families of apportionable matrices. We've added to these, but let's see. Let's say in the remaining minutes that we have, something about what we don't know and what I think we should know soon enough. These are problems that I think will be in the linear algebra textbooks that are going to be written in 2 years, thanks to one of your groups. But we have not been able to find the answer quite yet. Question 1, which I think is the easiest. Suppose I tell you that the matrix A is apportionable. You add a 0 row and a 0 column. You add a 0 row at the bottom of the matrix, you add a 0 column on the right of the matrix. Is that new matrix apportionable? Now the reason we are interested in this is because we know that if you add n rows and n columns, the answer is yes. That if you add enough rows of zeros and enough columns 0 to an apportionable matrix, you get a new apportionable matrix. So is it already true if you only add 1 0 column, 1 0 row? The guys should begs for an easy proof from the book or a counterexample, right? We don't know. Now the reason why if you add enough columns, you get apportionable is because we know that the tensor product of apportionable matrices has to be apportionable. So if you tensor product with a 2 by 2 matrix, you're basically adding n zeros and n rows. Everybody sees? Okay. So that's why I know that if you add enough zeros, columns and 0 rows, you get apportionability, which tells us that zeros help apportionability. We already know that rank 1 are U apportionable. But we also know that there are rank 2 matrices that are not apportionable. So the more close to invertible your matrix is, the least likely is apportionable. But there are counterexamples. I mean, the Hadamard matrix is completely invertible. So we know that in general, 0 help, but we don't quite understand how. So this is the first question. The second question is more algorithmic. I mean, my training is in computer science. What I want is a polynomial time algorithm for apportioning. So if I give you a matrix, and I give you a promise that is apportionable, what algorithm can you use to actually find the U? If I give you a matrix and I tell you it's diagonalizable, we have efficient algorithms to diagonalize it. Won't you expect that it's just as easy if I promise you that it's apportionable, that you'll find some combination of eigenvectors to produce the apportionable matrix? But we don't know the answer. And finally, the third problem is a certificate. When your matrix is not apportionable, what is the least value you can get? In other words, if you smear up to a point where smearing any more down is not possible, how do you certify it? How do I convince you that this this n that I found is the best you can achieve? There's no best. I do not know a polynomial time certificate for those. Okay, so these are the open questions that relate to apportioning that I think are manageable to solve, but not much is known. And the takeaway I want to convey is that diagonalizing seems to be easy. Concentrating the mass into the diagonal entries seems to be easy. But doing the reverse seems to be hard. Is there any fundamental reason that should be the case? Why we think it's hard is because it's connected to all these combinatorial problems that we do not know how to solve. An efficient algorithm for apportioning would solve all these combinatorial problems, so we should get a sense for why this should be easy, why this should be hard, and it sounds like a very natural problem. Change the soup into an inf, and it's the exact same problem that seems to be hard to solve. Okay, this concludes the talk. But I won't talk about hypermatrices. This concludes the talk.